Hello, very good day to everyone. In this case, I'm here to talk to you a bit about respiratory mechanics, which refers to the study of how air moves in and out of the lungs, and fluid dynamics, which is the science of how fluids like air and blood flow through the body. In this session, we will cover the main laws of fluid dynamics as they apply to respiration, including principles such as pressure, resistance, and flow, as you can see here in the slides. We are going to explore how the laws of fluid dynamics relate to respiratory physiology. Let's start with the key physical laws that regulate airflow and gas exchange in the lungs. We'll continue with Ohm's law in respiration, which tells us that flow equals pressure divided by resistance. Ohm's law in respiratory terms relates airflow to pressure and resistance. The formula is flow equals pressure difference divided by resistance. Just like in electricity, higher resistance or lower pressure reduces airflow. Next, we have Boyle's law, which states that Pond times 1 equals P2 times V2 at constant temperature. Boyle's law establishes that pressure and volume are inversely proportional. When we inhale air, the chest expands. It expands by increasing the volume and decreasing the pressure, which allows free air to enter. In this case, we also have Dalton's law of partial pressures, which tells us that the total pressure equals pressure 1 plus pressure 2, also depending on the pressures present. Dalton's law states that the total pressure of a gas mixture is equal to the sum of the partial pressures of each individual gas. This helps explain the gas exchange in the alveoli, where oxygen and carbon dioxide move according to their partial pressures. We also have the five subsystems of respiration, which are ventilation, external respiration, transport, internal respiration, and cellular respiration. The respiratory system is divided into five functional subsystems. Ventilation is the movement of air in and out of the lungs. External respiration is the exchange of gases between the alveoli and the blood. Transport refers to how the blood carries the gases used. Ventilation is the movement of air in and out of the lungs. External respiration is the exchange of gases between the alveoli and the blood. Transport refers to how the blood carries gases using hemoglobin. Hemoglobin. Internal respiration is the exchange of gases between the blood and the body cells. Finally, cellular respiration is the process by which cells use oxygen to produce energy. In this case, we have respiratory disorders, which can be obstructive, which involve increased resistance, restrictive, which involve reduced lung volume, and mixed, which are both obstructive and restrictive. Obstructive disorders such as asthma or COPD increase resistance in the airways. The airflow is reduced. Restrictive disorders such as fibrosis reduce lung expansion. The volume decreases. In mixed disorders, both resistance and volume are affected. According to Ohm's law, if resistance increases or pressure decreases, airflow will be affected. Here we also have the spirometry curve of volume over time. In a spirometry test, we measure how much air you can exhale and how quickly you do it. It is the total volume of air forcibly exhaled after a deep inhalation. As we see here, it shows us the FEV, which is the volume exhaled in the first second. The FEV to FEC ratio helps diagnose respiratory disorders in obstructive diseases. This ratio is reduced. Here we have the Hall-Haldane effect, increased oxygen, decreased affinity for CO2 in hemoglobin. The Haldane effect describes how the binding of oxygen to hemoglobin reduces its capacity to carry carbon dioxide. In the lungs, as oxygen binds to hemoglobin, CO2 is released and exhaled. This promotes efficient gas-gas exchange and is fully involved in the Bohr effect.